Hello, Refuge. Oh, wow. Oh God, it's gotten bigger. It's multiplied. Yes. Ta-da. Yeah, here it is. Ta-da. Okay. So new board, new series. We're doing K Theory 1.1. Yeah. K Theory was surprisingly popular in this poll I did in my Discord. So if you want to vote on what series I do next and chat with other fans and other fellow mathematicians, yeah, then join the Discord. It will be in the description. Anyway, yeah, I'm going to be doing K Theory, and I'm going to start with Topological K Theory, and we're going to introduce the first notations of K Theory. I'm going to assume you know what a vector bundle is. If you don't and you're curious about some of the properties of these things, I can make a small series on them, only if you want and only if you need, but yeah, I'm going to assume you know what that is and what the Whitney sum is. Right, so in topological K theory, one of the main goals is to compute K of X, some space X, for these interesting spaces X. Well, this will be interesting, and yes, I'll explain what K of X is in a sec. And one of the main goals is to develop tools for computing K of X. And we'll do that in this series. But before we move on to any of that stuff, what K of X actually is, well, we'll just start by looking at an abelian monoid M. And a monoid is just a group which doesn't have inverses. Now, if we have an abelian monoid M, we can associate an abelian group S of M with M, okay? And we have a homomorphism S, which takes you from M to S of M. It's a homomorphism of these underlying monoids, okay? Such that it satisfies this universal property, such that, okay, for any abelian group G, for some abelian group G, okay, there exists a unique F tilde, a homomorphism, which takes you from S of M into G, such that for some homomorphism F, which takes you from M to G, the following diagram commutes. Okay, so it's a simple triangle. It's a simple diagram. So we have S, which takes you from M to S of M. Okay? We have M going to G via F. And we have this unique F tilde, this group homomorphism, which takes you from S of M to G. And this diagram commutes. Okay? Okay, so of course there are many different ways to construct this group S of M, but of course they're all going to be same up to an isomorphism. So one of these ways is if we take the product M cross N, sorry, not M, N. Okay, so if we have this, then we can form the quotient group by the equivalence relation that Mn is equivalent to M prime N prime if and only if there exists a P such that M prime plus N plus P equals N prime plus M plus P. Okay, this is one of the constructions, and this S here, S of M is equal to M0. Okay, now one basic example of this group is the natural numbers. So if we have S, sorry, let me do this in purple, just so you don't think it's part of the definition. Okay, so if we have S, sorry, this is lowercase, this is the map. Okay, so if we have S of M, where M is the natural numbers, including 0, but I'm just gonna, so that they include 0. Then S of N is precisely the integers, okay? As you can check very easily, okay? Alright, now, there's a fundamental example of this. Okay, and this is going to be very important, this construction here, and this one here is a very fundamental example. Okay, so if we have an additive category L, well, it's normally denoted with some weird script letters, but I'll just call it L. If we have additive category L, okay, so we have this category L. We denote the isomorphism class and an object E in L of L. Then the isomorphism class of E is denoted E dot, like this, okay? Now, we can easily make L a monoid, and then we can use this construction to form the Grothendieck group, okay? Okay, so if we have this isomorphism class, we can define addition on these isomorphism classes. Okay, so if we have the isomorphism class of E plus the isomorphism class of F, this is equal to the isomorphism class of E Whitney sum F. And this is associative because as you can check extremely easily, E and then Whitney sum the quantity F Whitney sum G is isomorphic to E Whitney sum F and then that Whitney sum G. And there is E Whitney sum 0 isomorphic to E. Okay? So this is completely fine, and it's well defined because this depends only on the isomorphism classes of E and F. Okay. so we have this. Now, if we denote, okay, so if we just have a set of these isomorphism classes with this here, then we have an abelian monoid. So let's just let phi of x be the set of isomorphism classes of x. Okay, now this is a monoid with this operation here, and in this case, S of phi of x, okay, is the Grothendieck group of x. Now, with this, we have a very important example of this. So if we have delta x equal to the set of vector bundles over x, and x is a compact space, okay, then the Grothendieck group of this, which is normally denoted k of x, this is denoted k of x instead of s of phi of x, okay, so if we have k of delta of x is denoted k of x, and sometimes we'll have a denoted k of k of x, and sometimes if it's a vector bundle over R or complex numbers or something, then there will be a little r or c depending on what there is here, to avoid confusion. But yeah, this is just to avoid confusion. If you know the context, then this is perfectly fine. And as I said at the start of the video, during the series we're going to develop a lot of tools to compute k of x for interesting spaces x. And okay, so now we've got notation out the way and definitions, we can start to prove some theorems and give some examples of this. And here, ladies and gentlemen, is where the board gets really cool. Oh yeah, okay. So a quick remark about this group K of x is that it depends contravariantly on x, which means that if we have a homomorphism f, which takes you from x to y, induces a functor f star, which takes you from delta of x to delta of y to delta of x, okay? This is contravariantly, so, yeah, so induces this, or a homomorphism from k of y to k of x, okay, and it has the properties that g times f star is equal to f star times g star, okay, because it's contravariantly, this is because it's contravariantly, and the identity star, the induced identity, is just equal to the evidence. Okay. Now, using this remark here that it defends contravariantly, this observation, okay, we can define the reduced K-theory of X. Okay, so if we have, let's say, alright, so if we have a projection which takes you from X to a point P, then by this remark it induces a homomorphism alpha, which takes you from Z, the integers, isomorphic to K of P, into K of X. Now, the co-kernel of this, the co-kernel of alpha, of this, is denoted K tilde of X. And again, sometimes we write K R of X if the basic field is R and etc. to avoid confusion, but normally it's okay, depending on the context, of course. Okay. Right, so now we're going to prove a proposition, which will be quite important, because it will allow us to define an explicit construction for this reduced K-theory, which will be nice and helpful. Okay. So if we have a proposition, So, if we have gamma equal to this composition phi of X, now this is the set of this is the monoid of isomorphism classes of vector bundles on X, and that takes you via S to K of X, and then that takes you via beta to the reduced K theory on X. Then gamma is surjective, and gamma of the isomorphism class of E equals the gamma of the isomorphism class in F if and only if E Whitney sum theta n is isomorphic to F Whitney sum theta p for some trivial bundles theta n and theta p. Okay. So the first part is really easy. Okay, so proving its surjectivity is really easy. Because the proof. Okay, so surjectivity is easy because if we have let's say, well, surjectivity is easy with a couple of facts, which I'm not going to prove today, or probably ever on this series. I'm just going to take for granted. If we have the class, the class of theta n is 0, in the reduced K theory of X, sorry. Another fact I'm going to just take for granted in this case, any object in K of X can be written as E minus theta n, okay? Then we can define beta, we can have beta of E, the class of E, minus the class of theta n. Well, this is, well, because the class of theta n is just 0, is equal to beta of the class of E, and this is just equal to gamma of the isomorphism class of E. So, this is surjectivity proven. That's the first part of the proposition. Second part of the proposition, if we are just going to prove one-way round, so that when they're equal, that implies this. But the other way around is quite obvious. Okay, so I'm just going to use take another fact for granted for this theorem. So if we have gamma of the isomorphism class of E equal to gamma of the isomorphism class of some F, this is equivalent to saying, this implies that the class of E minus the class of F is isomorphic to the class of theta n minus the class of theta p for some n and p. Okay? Now, by this fact, which I'm going to use, which I'm again going to take for granted, by the fact that okay, in K of X, okay, the class of E is equal to the class of F if and only if E Whitney sum theta n is isomorphic to F Whitney sum theta p. Well, we can kind of add these things, so theta n for some n. Well, if we rearrange this slightly, this means here that E Whitney sum theta n Whitney sum theta Whitney sum theta p, Whitney sum theta r is isomorphic to F Whitney sum theta n Whitney sum theta r for some r. Now we can combine these two. So if we let theta, let's use sigma because sigma is obviously the best letter of all. And here we'll use mu because I don't know why. Theta mu. Oh crap, that's a terrible mu. Okay, that's the best mu you're gonna get. Sorry, mu prime. If you're watching mu prime math, I sincerely apologize for this terrible mu, which probably looks nothing like it. Anyway, sigma is equal to n plus r, and mu is equal to r plus p, okay? And this is proven, if you can just prove the converse yourself. Right, now we're going to finish the video with an explicit formula with this proposition here for the reduced K theory of X. The thing is, I haven't used, oh yeah, I just use it here. I'll use purple. Alright, so, we can define the reduced K theory of X to be the quotient is the quotient of phi of X, remember, from here. Oh, sorry, I didn't write it down. Phi of X is the is the monoid of isomorphism classes of vector bundles on X. So it's the quotient of phi of X with the equivalence relation the isomorphism class of E is equivalent to the isomorphism class of F if and only if there exist N and P such that E Whitney sum theta N is isomorphic to F Whitney sum theta P. Okay, and I mean, I've written down a lot of K theory in this introduction here. We've got this, which is quite a bit, and you know, well, this is just flexing now. we've got this as well. Okay, that's just great. I mean, this is just awesome. I could do this for days. Whee! Whee! Oh crap! We're still recording. Sorry. Yeah. This is just awesome. I'll see you in the next video, I guess. Bye. Where I'll be doing more K theory. Bye.